This code imports the TensorFlow library and assigns the name device_name to the result of a function that checks for the name of the GPU device on the system. It then uses the conditional statement to check if the name of the GPU device is not equal to /device GPU 0. If this condition is true, it raises an error indicating that a GPU device was not found on the system. Finally, it prints a message indicating the name of the GPU device that was found. This code uses the functionality of the Google Collaboratory platform to mount Google Drive within the program. It imports the Drive module from the Google.Collab library, and the first commented line indicates that it will prompt for authorization, presumably to access the user's Google Drive account. In the next line, the drive.mount function is used to mount the drive, and the argument /content/drive specifies where the drive will be mounted. The force_remount equals true parameter ensures that if the drive is already mounted, it will be remounted to the specified location. Overall, this code allows the user to access files and data stored in their Google Drive account directly from the program. The code begins by importing various libraries and modules that will be used later on. These include the __future__ module, which allows the use of features that will be in future versions of Python, the NumPy and Pandas libraries, which provide powerful tools for data analysis, the Matplotlib library, which is used for plotting graphs, and the Keras library, which is used for building and training neural networks. The code also imports specific functions and classes from some of these libraries. Next, the code changes the current working directory, which is the location where the code is being executed. This is done using the OS module. The main purpose of this code is to prepare the data for training a neural network. This includes data cleaning, normalization, and splitting it into training and testing sets. The code achieves this by importing the necessary libraries and using functions and methods provided by these libraries. Overall, this code is used to set up the environment for data analysis and build and train a neural network model. This code contains 4 separate functions. The first function, prettify_ax, takes in an axis object and makes it visually appealing by setting the spines, borders, to be invisible, setting the frame to be visible, adding a light gray background, adding a grid with white lines, setting the direction of the tick marks to be outward, and ensuring that the axis is below the other elements in the figure. The second function, simple_ax, creates a single visually appealing axis by creating a figure of a specified size and adding a subplot. It then uses the prettify_ax function to make the axis visually appealing and returns the figure and axis objects. The third function, earliest_date_after, takes in a query date and a list of ordered dates and finds the earliest date after the query date in the list. It does this by looping through the list and checking if the query date is earlier than the date in each index. If it is, the function returns that date. If there are no dates after the query date, the function raises an exception. The fourth function, latest_date_before, takes in a query date and a list of ordered dates and finds the latest date before the query date in the list. It also loops through the list and checks if the query date is earlier than the date in each index. If it is, the function returns the date before the current index. If the query date is earlier than all dates in the list, the function raises an exception. The last function, inv_price_transform, takes in normalized price data and a scalar object and returns the raw price by multiplying the normalized data by the scale and adding the mean. Overall, These functions serve as helper functions for manipulating and visualizing data and making the code more efficient and readable. This code is a set of functions that loads and merges different datasets related to stock prices, company filings, news articles, and market sentiment regarding a specific stock ticker. The code takes in the ticker symbol of a stock and uses it to load data from various files stored in specific locations. The data is then formatted and merged into one data frame called return_df, which contains the closing stock price, news articles, economic indicators, and market sentiment for a specific stock. The code also sets a start date based on the earliest date in the news coverage and clips any price data before that date. The code then iterates through the rows of the stock price data, aggregating all the data for that specific date and appending it to the return_df data frame. This process is repeated until all rows of the stock price data have been processed. The final output is a data frame with the stock price, news articles, economic indicators, and market sentiment data all in one table, organized by date. This data frame is then returned and saved as amzn_df for future use. The code is used to display the first few rows of data in the X data frame named amzn_df. In other words, it shows the information at the beginning of the amzn_df table. This can be helpful when first examining a large dataset, as it provides a quick overview of the data and its structure. The head function is a built-in method in Python that can be used to view the first few rows of a data frame. By default, it displays the first 5 rows, but you can specify a different number if needed. This code is used to prepare time series data for a machine learning model to predict stock prices. It starts by defining a function called load_stock, which takes in a data frame as the input and a parameter called lookback, which is set to 25 by default. Inside the function, the data frame is converted to a numpy array using the .values method. The function then calculates the index of the last row in the data frame and subtracts 365 days from it. This is used to determine the number of rows that will be used for training the model. Next, the data is normalized to have a mean of 0 and a standard deviation of 1 using the standard scalar from the preprocessing module. The normalization is only done on the training data, which is the data before the last 365 days. The data is then split into 2 lists, data X and data Y, which will hold the input and output values respectively for the model. The loop iterates through the training data and adds rows of length, lookback, to data X, while adding the stock price of the next day to data Y. This is done so that the model can be trained to predict the stock price based on the previous 25 days of data. The lists are then split into training and testing sets, with the training set containing all the data before the last 365 days, and the testing set containing the remaining data. The function then returns all the necessary data for model training, including the normalized data, x_train and y_train for the training set, and x_test and y_test for the testing set. Lastly, the function also returns the scalar, which stores the mean and standard deviation used for normalization in case the same scalar needs to be applied to new data in the future. The final lines of code use this function to load a specific stock, AMZN, and set the lookback parameter to 25. This will return the training and testing data along with the scalar, which can then be used to train a machine learning model to predict stock prices for the particular stock. First things first, we are normalizing the training and test price data, which means we are transforming the data into a standardized range so that it can be easily compared. This is important because the data may have different scales and it is necessary to make them comparable. Then, we have a print statement which displays the number of training and test examples that we have in the data. Next, we define a simple _x function with a figsize parameter that determines the size of the plot. This function returns a figure and an axis object. Next, we plot the training data with a blue line and the test data with a red line. The inv_price_transform function is used to transform the data back to its original scale. We then set the title of the plot to Amazon normalized stock price data and label the x-axis as day and the y-axis as closing price. Finally, we add a legend to the plot and display it. This code essentially visualizes the normalized stock price data for Amazon using a line plot. This code is used to train an LSTM, long short-term memory, model for forecasting stock prices of the company Amazon, AMZN. It starts by defining a sequential model, which is a type of neural network that processes data in a sequential manner. The LSTM layer is added to the model with a size of 128 units. Input shape is specified using the x_train dataset, which is the training data for the model. The return_sequences parameter is set to true, which means that the LSTM layer will return a sequence of outputs instead of a single value. This is useful when dealing with time series data. A dropout layer is then added with a dropout rate of 0.2, which is used to prevent overfitting. Another LSTM layer is added with the same size and a return_sequences parameter of false, meaning it will only return the last output. Another dropout layer is added, and finally, a dense layer is added with size 1, output layer, and activation function of linear. The model is then compiled with the mean squared error, MSE, as the loss function and the RMSprop optimizer. This means that during training, the model will minimize the difference between the predicted stock prices and the actual prices. The model is then summarized, showing the architecture and number of parameters. This code trains a machine learning model using the fit function. The first line initializes a variable, t0, with the current time through the time.time function. Next, the fit function is called on the model, passing in the training data, x_train, and corresponding labels, y_train. The batch_size parameter is set to 512, which means the model will update its weight values after every 512 training instances. The epochs parameter specifies the number of times the model will iterate over the entire training dataset. In this case, it is set to 200. The validation_split parameter indicates that 5% of the training data should be used for validation, while the remaining 95% will be used for training. Finally, the verbose parameter is set to 0, which means the training progress will not be displayed on the screen. Overall, this code trains a machine learning model and saves the training history in the history variable. This code consists of a function called model which includes two parameters. Based on the dataset, the function stores all the incomplete data on December 3, 2017 into model 0, and the complete dataset on December 4, 2017 into model 1. The function then proceeds to save model 1 in the specified location content/drive/my drive/collab notebooks/data/model1.h5. This allows us to save the complete dataset for later use or reference. This code is designed to help predict future prices. First, it imports the libraries necessary for data manipulation and machine learning. Then, it defines a class called regression that will contain all the functions and methods needed for the prediction process. The class constructor initializes various attributes, including the model type, data, and the model itself. The clean_data function is used to preprocess the data by removing unnecessary columns and dealing with missing values. The train_model function is responsible for training the model using the preprocessed data. Next, the predict function makes predictions on new data using the trained model. Lastly, the visualize function plots a graph showing the predicted prices compared to the actual prices, providing a visual representation of the model's accuracy. Overall, this code creates a framework for predicting future prices using machine learning algorithms. This code loads a previously trained machine learning model that has been saved in the specified directory. The model is stored in a file called model1.h5. Once loaded, the model can be used to make predictions on new data without having to train it again from scratch. This saves time and computation resources. Once the model is loaded, it can be used just like any other trained model to make accurate predictions on new data. This allows for easy testing and deployment of trained models. This code snippet is predicting the test set predictions for a model. It uses the test data, x_test, to make the predictions. The predicted values are then printed out along with the root mean squared error, RMSE, which is used to evaluate the model's performance. The code then uses the matplotlib library to create a graph that shows the predicted values in blue and the actual values in red. The graph is labeled and a legend is added to show which line represents the predictions and the actual values. Finally, the graph is displayed using the show function. Overall, this code is used to evaluate and visualize the performance of a model on a test dataset. This code defines a function named predict_days, which takes in 4 parameters: day, days_top_predict, data, and model. The purpose of this function is to predict stock prices for the specified number of days starting from the given day. First, the function assigns the current day's data to a variable, cur_data, by slicing the data array at the specified day index. This data is in the form of a 2D array with each row representing a day and each column representing a feature, e.g. stock price. Next, a list called predictions is created to store the predicted stock prices. Then, using a for loop, the function iterates over the specified number of days to be predicted and makes predictions using the given model by passing in the current day's data. The predicted stock price is then stored in the predictions list. After each iteration, a new row is created using the last row of the current data, and the predicted price is added to the first column of this row. The cur_data array is then updated by removing the first row and adding this new row to the end. This process is repeated for each iteration, resulting in an updated cur_data array each time. Finally, once all the predictions have been made, the predictions list is returned, containing the predicted stock prices for the specified number of days. This code first sets a variable called days to 30, indicating that we want to predict for 30 days in the future. Then, it creates a simple figure axis with a fixed size ratio of 10:6. Next, it plots the inverse price transformation of the test values, which are passed to a scalar. Then there's a for loop that iterates through the range of values from 0 to the length of the test values divided by the number of days we want to predict, in this case, 30. Inside the loop, the code calls a function called predict_days, passing in the segment index times the number of days, multiplied by the days variable, the number of days, the test values, and a model variable. This function is used to predict the stock price for the number of days specified. The predicted values are then plotted using the range of values for that segment, and the inverse price transformation is applied. After each iteration of the loop, two vertical lines are added to the plot indicating the start and end points of the segment. This is done using the .axLine function. Finally, the x and y labels and the title of the plot are set, and the plot is shown using the .show function. Overall, this code is used to predict and plot the projected path of stock prices for multiple days in the future, with a fixed number of days being predicted for each segment of the test values. The first function, _try_pred_true, is a function that takes in variables for the starting point, the number of days to predict, the data, the model, and a return threshold. It then uses the predict_days function to make predictions for future prices. Based on those predictions, it calculates the maximum and minimum prices, and then determines the return on buying or selling based on those prices. If the return on buying is greater than or equal to the return threshold, the function returns true, indicating that the market decision is to buy long. If the return on selling is greater than the return threshold, the function returns false, indicating that the market decision is to sell short. Otherwise, it returns none, indicating that no action should be taken in the market. The second function, _true_dates_pred, takes in variables for the data, the model, the return threshold, and the number of days to predict. It then creates two empty lists, one for true dates and one for sell dates. It loops through the data and uses the previous function to make market decisions at each time point. If the decision is to buy long, the time point is added to the true dates list. If the decision is to sell short, the time point is added to the sell dates list. Every 20 time points, it prints out a message indicating the progress. At the end, it returns the list of true dates and sell dates. Finally, the last line of code calls the _true_dates_pred function and passes in the necessary variables. The resulting list of true dates and sell dates will indicate when it would be best to buy or sell based on the given data and model. This code begins by importing a simple _x function and calling it with a figsize argument to create a figure and axis for plotting. The figure's dimensions are set to 10 by 6. This function also returns two variables, f and a. Next, the code uses the axis, a, to call the plot function and pass in the y_test and scalar variables, which contains the transformed stock price data. The c argument is used to set the color of the plot to black. This creates the main line plot for the stock price movement. The next two lines use the scatter function to plot additional data points. The first scatter call uses the true_dates and y_test variables to plot the actual stock prices on the graph, while the second scatter call uses the sell_dates and y_test variables to plot the dates on which the stock was sold. The c arguments are set to yellow, c equals y, and blue, c equals b, respectively. After plotting the data, the code sets the labels and title for the graph using the set_label, set_label, and set_title functions. This gives context to the data being plotted. The next line defines a list called rex that contains two rectangle objects with different colors, yellow and blue. These rectangles will be used as a legend for the graph, representing the true stock prices and the price movement respectively. Finally, the legend function is called to add the legend to the graph. It uses the rex list as input, and also sets the location and size of the legend. The plt.show function is then called to display the graph. In summary, this code creates a graph of stock price movement using various data points such as true stock prices and sell dates. It also adds a legend and labels to the graph for better understanding and visualization. This code is used to plot normalized stock price data for Amazon. First, it creates a figure and axis object using the simple _x function and sets the figure size to 10 by 6 inches. Then, it plots the training data and test data on the axis, using the inv_price_transform function to reverse the normalization process and get the actual stock price values from the scaled values. The plot for the training data is shown in blue, and the plot for the test data is shown in red. The title of the plot is set to Amazon Normalized Stock Price Data and the axis labels are set to day and closing price. Finally, the legend is added to the plot, and it is displayed using the plt.show function. This code is helpful in visualizing and comparing the normalized stock prices for training and test data. This code first creates a sequential model, which is a linear stack of layers. The first layer that is added uses the LSTM algorithm with 256 neurons. The input shape is determined by the shape of the training data, and the return sequences parameter is set to true. This means that the output of this layer will be a sequence, which will then be fed into the next layer. The next layer is added using the dropout function, with a rate of 0.2. This helps to prevent overfitting on the training data. The next layer uses the LSTM algorithm again, this time with 128 neurons, and the return sequences parameter is set to false. This means that the output of this layer will be a single vector. Another dropout layer is then added to the model, with a rate of 0.2. The final layer added to the model is a dense layer, which has only one neuron and uses the ReLU activation function. This function introduces nonlinearity to the model, making it more powerful. The loss function for the model is set to mean absolute error, MAE, and the optimizer is set to stochastic gradient descent, SGD. Finally, a summary of the model is printed, showing the layers that have been added and the parameters that have been set. This code sets the starting time to the current time and stores it in the variable t0. Then, it trains a model using the data in x_train, features, and y_train, labels, using a batch size of 512 and running for 100 epochs. It also splits the data into training and validation sets, with 5% of the data being used for validation. The verbose parameter is set to 0. Which means that the training process will not display any output to the screen. Overall, this code modifies the parameters used for model training and then trains the model using the new parameters. This code is used to save a model that has been created and trained for a specific dataset. The first line. Hashtag save model hashtag is a comment used to indicate that the following code is used to save the model. The next two lines, Model 0, December 3, 2017, incomplete data, and Model 1, December 4, 2017, complete dataset, are also comments that provide information about the model, such as when it was created and what type of data it was trained on. The next line, Model.save, content/drive/my drive/collab notebooks/data/model1.h5 is the actual code for saving the model. The model.save function is used to save the model to a specific location, in this case, the content/drive/my drive/collab notebooks/data folder. The model1.h5 in the parentheses is the name of the file that will be saved, and the .h5 extension indicates that it is a hierarchical data format, HDF5 file, which is commonly used for saving deep learning models. Overall, this code is used to save a trained model for future use, and it also provides some information about the model and when it was created. This line of code loads a pre-trained machine learning model with the name model1.h5. The location of the model file may vary, but in this case it is in the data folder, inside the Collab Notebooks folder on your Google Drive. This step is necessary if you want to use a pre-trained model for prediction or further training. By loading the model, you can access its architecture, parameters, and other necessary information for making predictions. This code is used to compare the actual stock prices with the predicted stock prices using a machine learning model. The first line uses the model to make predictions on the test data set, which is stored in the x_test variable. Then, the root mean squared error, RMSE, is calculated for the predicted values compared to the actual values, stored in the y_test variable. The next few lines are used to plot the predicted and actual values on a graph, with the predicted values shown in blue, and the actual values shown in red. The axis labels and title are set to describe the data being plotted. Finally, the graph is displayed and a legend is added to show which line represents which set of values. This code can be used to evaluate the accuracy of the machine learning model in predicting stock prices and visually compare the predicted and actual values. This code is basically a function that predicts stock prices for a given number of days using a certain model. The function takes in 4 parameters: start day, days_predict, data, and model. First, the code initializes a variable called cur_data and assigns it the value of the data at the index given by the start day parameter. This essentially selects the data for the first day that we want to make a prediction for. Next, a list called predictions is initialized. This list will store the predicted stock prices for each day that the function loops through. A for loop is then used to loop through each day that we want to make a prediction for, based on the days_predict parameter. Within this loop, the model is used to make a prediction based on the current data. This prediction is then added to the predictions list. At the end of each loop, a new row is created based on the last row of the current data. The first value of this new row is then updated with the prediction made by the model. This new row is then added to the current data, essentially shifting the data by 1 day and replacing the first day's data with the predicted value. Once the loop has finished iterating through all the days, the predictions list is returned as the final output of the function. The code is used to predict and plot the stock price of Amazon for multiple days in the future. It first sets the number of days to be predicted as 30. Next, it initializes a plot with a specific size of 10 by 6. Then, it plots the actual stock price of Amazon by transforming the price with a scalar. Next, it goes through a for loop where it iterates over the segments of the test set, with each segment being equal to the number of days predicted. Within this loop, It predicts the stock price for the next 30 days using the model. Then, it plots the predicted prices for each segment and adds vertical dashed lines to indicate the end of each segment. Finally, it adds labels and titles to the plot and shows it. This code is a function that takes in 5 parameters: start point, days underscore to predict, data, model, and return underscore threshold. It uses these parameters to predict future prices and make a market decision. The predict underscore days function is called with the given parameters and the results are stored in a list called predictions. The first value in the predictions list is used to calculate buy return and sell return, which represent the potential profit from buying long and selling short, respectively. If buy return is greater than or equal to sell return and also greater than or equal to the given return underscore threshold, the function returns true, indicating that it is a good decision to buy long. If sell return is greater than buy return and also greater than or equal to the given return underscore threshold, the function returns false, indicating that it is a good decision to sell short. If either of these conditions are met, the function returns none, indicating that no action should be taken. The underscore true underscore dates underscore pred function is then called, which takes in 4 parameters: data, model, return underscore threshold, and days underscore to predict. This function uses a for loop to iterate through the length of the y underscore test data. Within the loop, the underscore try underscore pred underscore true function is called with the current iteration number as the start point parameter, and the other parameters remaining the same. Depending on the result of the underscore try underscore pred underscore true function, the current iteration number is added to either the true underscore dates or sell underscore dates list. Every 20 iterations, a message is printed indicating the progress of the data walk. Once the loop is complete, the function returns the true underscore dates and sell underscore dates lists. These lists represent the dates where it would be a good decision to buy long or sell short, respectively. The code is then called using the x underscore test data, with a return underscore threshold of 0.5 and a prediction of 30 days into the future. This modified code is based on code found on GitHub that uses dynamic programming to make optimal buy-sell decisions in the stock market. This code first imports a function called simple underscore x and sets 2 variables f and a equal to the output of this function. This function sets up a plot with a specified figure size. The next line then calls the plot method on the a variable and plots the transformed y underscore test values, with the color set to black k. The following 2 lines then use the scatter method to plot the true and sell dates, also using the transformed y underscore test values. The true dates are plotted with the color yellow, y, and the sell dates are plotted with the color blue, b. This gives us a visual representation of how the stock price has changed over time. Next, the code uses the set underscores label and set underscore label methods to label the x and y axes, and the set underscore title method to set the title of the plot to stock price movement with LSTM using sentimental analysis. The next line creates a new object called rex, which stores 2 rectangles with specified colors, y and b. Finally, the code uses the legend method on the a variable to add a legend to the plot, with the labels true and price movement, and sets its location and size. The last line then displays the finalized plot. In summary, This code is importing a function to create a plot with a specified figure size, plotting different data points on the plot to visually represent stock price movements over time, and adding labels and a legend to the plot for clarity.